electron spin resonance or electron paramagnetic resonance. Like NMR, ESR is also a magnetic resonance based spectroscopic technique. The basic difference is that in NMR, nuclear spin resonance occurs, but here in ESR, it is the unpaired electron resonance that is taking place. Moreover, the nuclear magnetic resonance occurs in the radio frequency region of the electromagnetic spectrum, while the electron spin resonance occurs in the microwave region. ESR spectroscopy is based on the fact that the molecules possessing unpaired electrons absorb microwave radiation in an applied magnetic field, causing the electron spins to flip. A typical ESR instrument is composed of three basic units: a microwave unit, a magnet, and a spectrometer. And in the microwave unit, microwaves are generated and passed through the sample containing unpaired electrons. And in the magnetic part, a strong magnetic field, say of several thousand Gauss, is applied, and the spin energy levels of the electrons get separated from each other. In the spectrometer part, the microwave photons absorbed by the unpaired electrons are amplified and finally recorded in this unit. Now, what can we study with the help of ESR spectroscopy? ESR is mainly used for paramagnetic substances, that is, the species that contain unpaired electrons, like the free radicals of biological species or any other naturally occurring free radicals. ESR spectroscopy can also be used for transition metals or their complexes in order to understand their probable geometries and all. Here, it is important to note that diamagnetic substances cannot be studied with the help of ESR. It gives an idea what kind of nuclei are present nearby the unpaired electrons. Now, applications of ESR. Here are some of the important areas in which ESR spectroscopy find its application. Like it is used to understand the electronic states, such as in magnetic materials as well as in semiconductors. Then for tracking of catalytic reactions, for oxidative degradation of lipids such as food oils, petroleums, etc. Then inactive oxygen radicals related to aging in living organisms, in the determination of the age of fossils, and also in order to understand photocatalytic reactivity and photochemical reaction mechanisms, etc. As we all know that atoms are made up of a positive nucleus located at the center and is surrounded by a cloud of electrons. These negatively charged electrons revolve around the nucleus exactly in a similar fashion as the planets do around the sun in our solar system. So while revolving around the nucleus, these electrons also rotate around their own axis. Here we can see how the electrons are revolving around their own axis. Due to this rotation of electrons around their own axis, they behave like teeny magnets. As we know that when a charged particle rotates, it generates a magnetic field like the other magnets. So this figure shows how the rotating electrons are generating magnetic lines of forces, resulting in the net magnetic field. In a similar way, the protons with a positive charge along with the spinning activity also behaves like a teeny magnet. Now, what could be the possible interactions that can take place in the ESR spectroscopic technique? Actually, there are three main interactions that can be expected in this particular technique. Firstly, when an external magnetic field is treated with the unpaired electrons, splitting of the electron spin states will take place. which is known as the electron Zeeman effect. Similarly, if the interaction is taking place between the nuclei and the external magnetic field, splitting of the nuclear spin states will take place, which is known as the nuclear Zeeman effect. And when there occurs interactions between the nuclei and the electrons, the so-called hyperfine splitting takes place. Electron spin state or spin quantum state. So the two up and down arrows in this figure represents two electronic states or spin quantum states of the unpaired electron. This upward arrow has the ms value of plus half, and this downward arrow has the ms value of minus half. And in the absence of the magnetic field, the energy of these two quantum states is equal, or we can say that these quantum states are degenerate. Now let us see how an external magnetic field affects the two spin states. For this, let us consider a species with an unpaired electron in an external magnetic field of strength B naught. So here we can see that in the absence of the magnetic field, that is when B naught is equal to 0, the two spin states of the unpaired electron are degenerate. Now, when an external magnetic field of strength B naught is introduced, the spin states will no longer remain degenerate and will be split up into two energy states. One will be lowered in energy, the other will be raised in energy. The lower energy state will be known as the beta state, and in that particular state, the magnetic field generated by the unpaired electron will be aligned parallel to the external magnetic field. And on the other hand, the higher energy state will be known as the alpha state, and in which in this particular state, the magnetic field arising from the electron will oppose the external magnetic field. That means it is anti-parallel. The energy difference between these two quantum states is given by del E is equal to G mu B into B naught, where mu B is the Bohr magneton, B naught is the strength of the external magnetic field, and G is the Landé splitting factor. This G value can be compared with that of the chemical shift in NMR spectroscopy. And for a free electron, this G is represented as ZE and is equal to 2.0023. But when the electron is a part of the molecule or a compound, Z is not equal to ZE, because in that case, the unpaired electron will be surrounded by some local magnetic fields arising from other magnetic nuclei and results in the spin orbital coupling. The ESR technique. So as we have already discussed, that electron Zeeman effect is the interaction between the magnetic field generated by the unpaired electron and the external magnetic field of the instrument. So this interaction gives rise to the ESR signals. The classical interpretation of this effect is that it occurs between the magnetic field arising from minus half spin state of the electron aligned parallel to that of the external magnetic field, and its energy goes on decreasing with the increase in the field strength. On the other hand, the plus half spin state aligned against the external magnetic field, so the energy increases with the increase in the field strength. And in the ESR experiment, constant energy microwave radiation is sent in, while applied magnetic field is varied. The strength of the magnetic field is increased until the separation between the quantum state matches the energy of the microwave. When energy of separation between the two states matches the energy of the microwave photon, that is h nu, a signal appears, and that corresponds to the flipping of electron spins. Now, how to record the ESR spectra? The ESR spectra are commonly presented as the derivative curves. That is, it is a plot of first derivative of the curve absorption against magnetic field rather than the absorption curve itself. And this arrangement is used because it gives a better signal to noise ratio than a simple plot of absorption against magnetic field. Now, for the calibration of the ESR spectra, a free radical called DPPH, that is diphenyl picaryl hydrazine, is used as a reference. It is quite similar to that of EMS, trimethylsilane, used in the NMR spectroscopy. The Z value for DPPH is almost 2, as that of the ZE value, which is obtained for the free electrons, and it gives one very fine signal in the ESR spectrum. Now, the selection rules. For all the spectroscopic techniques, one of the most important aspects is the selection rule. So obviously, a ESR technique is also having some selection rules. The selection rules for ESR depend upon mainly two factors. One is the electron spin and the other one is the active nucleus or the magnetic nucleus, which is present in the sample. So for molecules in which only unpaired electron is present and no active nuclei, selection rule will be del ms is equal to plus minus 1. And for systems with only active nuclei, selection rule will be del mi is equal to plus minus 1. But when both the unpaired electron and active nuclei are present together in a system, the selection will have to follow two conditions. First one is the del ms value should be equal to plus minus 1 and the del mi should be equal to 0. Now, there is a simple rule to check whether a given nuclei is active or not. And according to it, only those nuclei will be treated as active nuclei whose mass number is not divisible by 4. For example, carbon, say carbon. Carbon with mass number 12 is not an active nucleus. However, nitrogen with mass number 14 is an active nucleus. Now, let us consider a single unpaired electron. In the absence of the external magnetic field, the two spin state will be degenerate. That means both the plus half and minus half state will have the same energy. Here we can see that under the influence of a magnetic field, but in the absence of any active nuclei, splitting of these two states take place. That is, the states plus half and minus half will be separated from each other. Now, if that single electron is present in a species along with an active nucleus of spin half, these two states undergo further splitting, giving rise to a total of 4 energy states. The order of these energy states are shown here in this figure: plus half, minus half, and plus half. So here, if we follow both these two conditions together, that is del ms is equal to plus minus half and del mi is equal to 0, then two allowed transitions will be observed, and hence two ESR lines. Now, calculation of hyperfine ESR lines. The number of ESR lines can also be obtained by using a simple formula, that is twice Ni plus 1, where N is the number of active nuclei present in identical chemical environments. That means equivalent nuclei. Then I is equal to nuclear spin. So the formula will tell us about the number of ESR lines or hyperphi lines in a given molecule. Now, if the hyperfine splitting is caused by both a set of n equivalent nuclei of spin Ia and a set of m equivalent nuclei of spin Ib, then in that case, the total number of lines will be given by this formula, twice n Ia plus 1 into 2 twice m Ib plus 1. Similarly, if we have two sets of equivalent nuclei, suppose one set consisting of n equivalent nuclei and the other set consisting of m equivalent nuclei, but with the same nuclear spin of value I, then the total number of ESR lines will be equal to twice n I plus 1 into twice mi plus 1. Now, the relative intensity of the ESR lines can be obtained by using the Pascal's triangle. This is the Pascal triangle. For relative intensities, the number of lines present in an ESR spectrum follow the corresponding row in the Pascal's triangle. For example, if a molecule shows 3 ESR lines, its intensity will be 1:2:1 as per the third row of the Pascal's triangle. Here you can see 1:2:1. So when we get 3 ESR lines, then the intensity of the lines will be 1:2:1. Likewise, if we have 5 ESR lines for a given species, then we'll have to follow the fifth row of the Pascal's triangles, which will give us the intensity of the lines, that is 1:4:6:4:1. Similarly, if you go for a species with 8 ESR lines, then you'll have to follow the 8th row of the Pascal's triangles, 1:7:21:35:35:21:7:1. And in this way, depending upon the number of ESR lines observed in a given sample, we can estimate the relative intensities of those lines. However, this rule is applicable only when the nuclei possesses spin value of half. For other nuclei, separate rules to be followed. So this particular rule is applicable for those nuclei having spin of half only.